Hello, everyone. I'm Bill Gervasi, the Principal Systems Architect for Nantero, and I'm one of the chairmen of the JEDEC Standards Organization. And what I'm going to present today is an overview of a new solid-state drive standard from JEDEC for automotive applications. So let's talk about the agenda for the discussion. We're going to talk about the cars and the requirements for these cars. And then we're going to focus in on what's needed in a solid-state drive for cars. Going to talk about the new JESD 312 standard and give you some insights into what's in this new standard. And then we're going to close up with, now that we have this new infrastructure in place, where do we go from here? So let's start with a high-level view. Automotive electronics used to be kind of a second thought. You took whatever parts from other industries, screen them a little bit and put them into cars, but now it has become a major market of its own with a compound annual growth rate nearly 10%. It's caught the attention of a lot of suppliers because they have all these variety of requirements from multiple input sensors, displays all around the vehicle. You have networking requirements and communications, maps and traffic. That aggregate data bandwidth can be upwards of 300 gigabytes per second. Now, let's focus in though on the storage requirements for these cars, and they tend to be a little bit more mainstream, like 128 gigabytes up to 4 terabytes. Now, the cars with all of this electronics going on, sensors and displays and so forth, there's not just a single main CPU that drives everything. It's now been broken up into what I show here is 4, but sometimes this could be 8 or even 10 different SoCs, all operating on different aspects of the automobile's data. What's new is that these are now being networked in through PCIe to a shared resource. And this is where the new standard is going to focus, is what is required for a PCIe-based solid-state drive. Well, we recognize that it needs to have pretty high performance. It needs to operate over a wider temperature range than you're normally used to. The expectancy for life is very long for these devices, yet we need very high security, and all this needs to be at a reasonable price point, multiply sourced from multiple suppliers. And that's the advantages of a JEDEC standard. You bring together the requirements of the industry into one specification and make it standardized so that you can get multiple sources from multiple vendors. The standard covers things like what is the package and what's the pinout of that package, the electrical interface into the device, what are the command protocols that it needs to support, what are the security levels that it needs to support. We're going to talk a little bit about something new, which is the idea of different storage regions within the drive. And finally, that ties in with what is the endurance requirement for such a solid-state drive. So let's start with the package. The package is from the PCI SIG. It's a 28 by 28 millimeter package, which gives us sufficient power delivery. And we talked about having a standardized heat spreader, but the feedback from customers were, no, leave the heat spreader to a system level solution, just expose the package so that it can be integrated into a holistic cooling system. Now, to give lots of options from 128 gigabytes through 4 terabytes, we want to offer a variety of packages. And this allows for the vendor to incorporate the number of die that are needed, any kind of on-chip voltage regulation, whatever is needed in these packages. And you start with the end user putting in a full 28 by 28 millimeter footprint, but then you can take multiple package types, like the 16 by 20 millimeter package, and drop that into the inner part of that landing pattern. The 24 by 20 is a little bit larger. It uses more of that common footprint. 22 by 28 millimeters, a little bit more. And finally, the 28 by 28 uses all of the pads and takes up the largest space. So with this variety of packages, you can see that suppliers can offer many different configurations to meet various customer needs. From the electrical standpoint, it's PCIe 4.0 based with a by 4 interface, which gives 32 gigabytes per second of peak throughput. In addition to the main data interface, it standardizes the system management bus and also the testability requirements for this interface with these SM bus and JTAG pinouts. Now, the command protocol is required to support PCIe 4.0. It's required to support NVMe 1.4C or greater. Also required are the SM bus and the JTAG interfaces. And not required but encouraged is a single root IO virtualization. You know, as I mentioned, there's a lot of SoCs that are sharing this device. So having SRIOV would be a pretty nice feature to have so that it simplifies the system management for the various SoCs. Security is critical for these devices. I mean, clearly none of us want our cars to be hacked while we're driving them. So SPDM is the security protocol and data model. This is an industry standard that has been adopted in here, where you have requesters and responders that are reviewed through a authentication algorithm. Now, being forward-looking, we are taking seriously the NIST recommendation that we move towards a minimum security level of 384-bit signatures and hash algorithms. Also, firmware resilience is part of this standard. If this device is in the middle of an update and a power fail occurs, you don't want that firmware to cause your car to be unable to reboot. Another optional feature is the idea of splitting the device into multiple storage regions. The bulk storage region is obvious. That is your standard storage for entertainment options and so forth. But the car designers are also very interested in having a higher security, higher reliability boot code section. And this is where the operating system and critical apps would be stored. Now, the smaller drives are not required to incorporate this. The larger drives, it is recommended that you have such a region and that it's a certain percentage of the overall drive requirements. As you can see here, say 32 gigabytes minimum for a 512 gigabyte drive, increasing maybe to 64 gigabytes for a 2 or 4 terabyte bulk region. Now, the distinction between the bulk storage and the high reliability system storage area is that they may have different reliability characteristics. The example that I show at the bottom there is the terabyte write for the system region might be different than for the bulk region. Now, some of these requirements are segmented by the market because not all market segments for automotive are equal. For example, a personal car is you leave time for vacations and so forth, but there's a lot of commuting going on, maybe 344 days out of the year that this car is going to be used, but it's only going to be used on average around 3 hours a day. Also, individual car owners may or may not have a schedule for regular maintenance and replacement of parts, so the drive lifetime requirements are a little longer at 15 years. Now, if you're driving a semi, this semi is going to be on the road essentially every day of the year, and it's going to be on the road for half of the day, 12 hours a day. But these vehicles are going to have regular maintenance schedules where parts can get replaced, including the SSD. So here, now we can see that the lifetime requirement is reduced from 15 years to 8 years. So how do these differences manifest themselves in terms of the drive? Well, I throw a couple of examples out there. So for example, if you look at a personal automobile, maybe with a 64 gigabyte capacity, you have a terabyte write factor of 12.8. Now this translates to a drive writes per day at 344 days a year, 3 hours out of every 24. You get a DWPD of 0.31. Contrast that to a professional auto, a semi, for example, where you might have a terabyte of storage, which has a 200 TBW. The drive writes per day on this calculate out to a different number, a minimum of 0.24 drive writes per day. So this is where the market starts to segment itself in terms of the application space. Now, what is the data utilization going to look like? Well, as I was describing, these cars are becoming supercomputers on wheels. It turns out that the data payload expectations are really, really close to the enterprise model. We looked at defining models specific to cars, but it turns out to be essentially identical to the enterprise model. So this specification points to JESD 218 and JESD 219, which are two other JEDEC standards for endurance requirements and test methods. And these are based on the enterprise model. So it took a while to gather all these requirements and get an agreement. But finally, the standard all came together in June of this year. And so the new JEDEC standard is now in the process of being reviewed for final publication later this year. But now I want to go on a little sidetrack. And this involves a personal story of being on a business trip up to the Bay Area, being in a rental car. And I was driving down Interstate 280, obviously obeying the speed limit of 65 miles per hour, when it was raining. And I was listening to music as I was going down 280 when a lightning bolt struck immediately to the right of me, about 50 feet away from my car. Screen went blank, the radio stopped, and while I was driving at 65 miles per hour, the car had to reboot. And this took about 7 seconds before my link showed, before the radio turned on, and before I could see the display on the car. And so this personal lesson affected me in terms of what was my car doing during those 7 seconds? Did I have steering? Did I have braking? I just kept my hands on the wheel and didn't do anything during that reboot time. This showed me the value of instant on and how important it will be for us to take these electronics in the next generation and start thinking about what it is that we really want out of these cars. How do we get to instant on? And so now that we have this PCIe based infrastructure, I'm sure you've attended a lot of talks at this conference on what's the next generation of PCIe. And one of the variations of PCIe in process is CXL, memory class storage. So the idea that the CXL protocols could be put onto this PCI switch is something that I'm starting to promote today, and I'm going to be talking about with the industry over the coming years in terms of how do you take that shared storage resource and expand it with shared memory resources. Migration to CXL would enable cars to implement this instant on. If you had a memory class performance on your centralized storage, these SoCs could have rebooted instantly, been running the critical apps that are stored in that memory class storage, and could have been essentially rebooting right away instead of taking that 7 seconds. And that's where my personal experience is affecting my views of where the industry needs to go. The key thing is that leave it in place data and even the potential for execute in place gets enabled when you can transition to CXL-based environment. And it improves that fabric coordination where the SoCs can now use that shared memory resource to communicate between themselves as well. So this is the subject of another talk at Storage Developer Conference. So please come to the other talk, a persistent CXL memory module with DRAM performance. So let's recap what we just talked about. These self-driving cars are going to be moving a phenomenal amount of data, and that this new generation of PCIe-based solid-state drives for cars, this is coming. JEDEC coordinated with multiple organizations to create this standard. We communicated with PCI-SIG, for example, with NVMe and so forth, to make sure that we were in synchronicity on the direction for the industry. And the JESD 312 specification combines this interoperability between vendors with optional innovations that each vendor can put to their devices. Finally, this is a moving target, the adoption of PCIe for the auto fabrics. This enables a future with CXL expansion characteristics that I think can add whole new levels of capabilities to the next generations of cars. And with that, I'd like to conclude and thank you for paying attention, for your inputs, and I look forward to chatting with you offline. Also remember, they'd like to rate these sessions so that we can make them better in the future. Good day.